Welcome back, everyone. If you would go ahead and take your seats, we'll get our last award session started. It's not the last session of the conference, by the way. There's still a little bit more. The Oersted Medal recognizes those who have had an outstanding, widespread, and lasting impact on the teaching of physics. The medal is named after Hans Christian Oersted, the Danish physicist and chemist who's credited with the discovery that electric currents create magnetic fields. This insight, known as Oersted's law, is a foundational principle of electromagnetism. Oersted is also credited with producing elemental aluminum for the first time and maybe the first modern thinker to explicitly describe and name the thought experiment. Barbara Whitten is an emeritus professor of physics at Colorado College. During her time there, she developed several innovative classes with real-world relevance, such as those involving sustainability and improving energy efficiency in housing, and was a founding member of the Women and Gender Studies program. Although Barbara has an impressive list of experience and publications within molecular and atomic physics, and more recently within computational environmental physics, it is for her substantial work in improving diversity and inclusion within physics departments that she is recognized today. As one of her nominators noted, when thinking about ways to increase the numbers of women and other underrepresented groups in undergraduate physics programs, instead of guessing what might be the correct approach, she decided to ask. Site visits, extensive interviews, and eventually NSF funding to support this research led to publications such as Physics Today's 2003 seminal article, What Works for Women in Undergraduate Physics? An additional project of Barbara's was the development of the Physics for Everyone curriculum, in which undergraduate students helped develop physics problems that were embedded in real-world contexts that promoted participation in physics by traditionally underrepresented groups. More recently, Barbara is a co-PI on the NSF-funded AAPT E-Alliances program for mutual mentoring of women physics faculty, an outgrowth of a mentoring collaboration developed with 3 other women faculty at liberal arts colleges. In the words of her second nominator, Barbara has altered the direction of how we discuss inequalities in our teaching practice by changing our focus from diversity to inclusiveness, and she has championed the role of the community in the education and professional development of physicists. For all these contributions to physics education, AAPT is proud to present the 2018 Oersted Medal to Dr. Barbara Whitten.
Hello? Excellent. All right. Thank you, Janelle. I realize now that I should have changed the title on this slide because I called it diversity, and apparently I should have called it inclusiveness. Sorry. I could begin this by thanking my parents and my children and my colleagues and my students, all of whom have contributed materially to my career. But I want to start by thanking Hans Christian Oersted, who discovered that electric currents cause magnetic fields, create magnetic fields, and invented the field of electromagnetism, pulled those two fairly separate things together. I also want to thank the American Association of Physics Teachers, not just for honoring me, but for honoring the idea of diversity and inclusiveness. I think this is an award for all of us who have tried to change the nature of our community, and I'm very proud to be representing it. I also want to thank Ann Cox and Juan Burciaga, who nominated me. And I'm proud to be in such distinguished company. These are 5, they're not exactly randomly chosen people. I went down the list of Oersted Medal winners and picked 5 people that I thought were interesting and that I like. As I was doing that, if I counted correctly, I think I'm the 4th woman to receive this prize since 1936. So I'm quite proud of that as well. My subject is really why do we care, or should we care, if we don't, about inclusiveness in physics? We're not the only ones who wonder about this. John Roberts, the Chief Justice of the Supreme Court, when he was hearing arguments about Fisher versus the University of Texas, one of many affirmative action cases that have come before the Supreme Court, asked, what unique perspective does a minority student bring to a physics class? And clearly, he was thinking what many of us think, that the culture of physics is the culture of no culture, that it doesn't matter who you are, that physics is physics. And I want to try to argue that that's not so. I think there are three basic reasons for us to care about diversity in physics. The first one I called equity, and it's really an individualistic thing. I, like perhaps many of you, think it's a dreadful tragedy if someone wants to be a physicist and can't. Okay? Maybe everybody doesn't think that, but I certainly think that. So I think we should be sure that everyone who wants to be a physicist and has the talent and persistence and so on should be able to do that. We shouldn't be prevented by silly things like gender and race and disability status and so on. That's the first reason. The second reason is often referred to as manpower. I think that's inappropriate in this context. So I've called it community, and that is what benefit does the community have if we have a broader representation? Well, there's a clear reason. Everyone knows that records are always broken because as the community of athletes grows with time, you have more and more people and you have better and better people. So if we broaden the pool of people that we can draw on to be physicists, we will improve the community. We will have better physicists. Okay? And the third one is, I think, the most interesting and the one I'm going to talk about, and that is not to look at the community itself, but to look at the physics we do and to ask, what effect does the homogeneity of the physics community have on the physics that we do? Okay? So let's start with just, I know you all know these numbers, but let's just start so that we're all on the same page with some numbers that will demonstrate the extent to which physics is a white male-dominated community. These are all NSF numbers from 2014, which is the most recent numbers that they have available. The top bar graph shows you, let me see if I can make this work, yes. Okay, this shows the percentage of people, of women receiving doctoral degrees going from 0 to 100%, and for different fields. Top one is, I need to do this with my right hand. The top one is all fields, and you can see that roughly 50% of doctoral degrees in all fields were offered to women. It's a little bit more if we look at the social sciences, and a little bit more if we look at the biological sciences. Engineering has about 23%. I can't quite see these. Math has about just under 30%. Chemistry has just under 40%. Physics has about 18% women. So even by the standards of our related sciences, math and chemistry, we have a very male-dominated community. If we look now at the variable of race, this is the percentage of doctoral degrees. This graph only goes to 60% because you couldn't see Native Americans if it went all the way to 100. This over here is white students receiving doctoral degrees. This is Black, Hispanic, Native Americans, and Asians. And you can see that, oh, one more thing. The red is all fields, the blue is physics. So one thing to learn is that academia is a very white-dominated community in all fields. About 50% of doctoral degree recipients are given to white students. Most of the rest, you can see from this graph, are not given to students of American ethnic minorities, but to students who are not American citizens. Okay? Physics has a slightly smaller percentage of racial minorities than other fields, averaged over all fields, and a slightly smaller percentage of white students because we have more international students in physics. Okay. Now, if we look not at the beginning of a career, but at the culmination of a career, the Nobel Prize in Physics has been awarded to 206 people between 1901 and 2017. In that time, 2 white women have received the Nobel Prize, Marie Curie in 1903 and Maria Geppert-Mayer in 1963. 19 Asian men, mostly Japanese, have received the prize, and 185 white men have received the Nobel Prize. So again, we have a very white male-dominated community of physicists. Okay. We have been, many of the people in this room, among others, have been studying the underrepresentation of women and minorities for about 40 years. And we have proposed many potential solutions or potential answers. Why is the physics community so white male dominated? Or kind of looking at the inverse, why are women and members of minority groups so underrepresented? A popular explanation, I should say also that most of this focuses on gender differences because there's been much more research on that. So there's much more data available, and it's what I've studied more than anything else. So this mostly focuses on gender. A popular explanation early on was biological differences between men and women. You know, women aren't as good at math, men are better at three-dimensional visualization, women are not as aggressive and therefore less competitive in the field of physics, all sorts of things like that. Those have faded out, at least in the literature, because the data that supports it is actually pretty scanty. And I think that a lot of us still kind of believe these things. So I don't think they've faded out in our minds, but they have certainly stopped being cited in the literature quite as much as they used to. Women do, in fact, come to college with less academic preparation than men do. The percentage of students in high school physics is about half girls, but girls tend to take lower level physics classes. So if you look at IB or advanced placement physics classes, you see more boys than girls. So girls do start college with less technical preparation in physics. And because of the structure of our undergraduate curriculum, you pretty much have to make up your mind in high school that you want to major in physics. It's very difficult to hop in at a later time. Because the field is so white male dominated, there is a significant lack of female role models, so girls don't know where they're going. The science curriculum designed by white men for white men is often less interesting to women and members of minority groups. And science pedagogy, also the impersonal and kind of stage on the stage model of traditional physics pedagogy favors male students. Many people have talked about the chilly climate for women in physics. This covers lots of things that make it difficult for young women to see themselves as succeeding in physics, to developing an identity as a scientist, and to feel like they belong in the community. Gender role socialization steers women toward more service-oriented, less geeky kinds of fields. And feminist theorists have argued that the epistemology of science is inherently masculine. Okay, that is our emphasis on objectivity, our idea that physics is physics no matter who does it, those kinds of things are inherently masculine. Now, when I started reading this stuff, I thought, oh, right, these are people who don't understand physics. And I think that's true, that they don't understand physics, but I think we can actually learn from them. We have been trained in physics. We're kind of, by definition, people who are successful in this community. And so this seems normal to us. And I think by learning what people who are not physicists think about our community and our subject, we can learn things that are useful and interesting. So I urge you to set aside your prejudices and try this. Okay. If we look now at the underrepresentation of minority students, this is a shorter list because much less research has been done. But you can also see that many of the causes are cultural. I think this is historical, that people started doing research on minority groups in physics around the time that the biological explanations were becoming less fashionable. So they tend to focus on cultural issues like stereotype threat, the lack of role models, the fact that the subject matter is often irrelevant, and conflicts with cultural and gender roles. You can see that the ideas are parallel. There's some of the same things that worked with, that people have studied where women are concerned. People are also studying where members of minority groups are concerned. I find this a little bit discouraging, but I think it is true that this extraordinary amount of research, very complex experiments, some of them quantitative in their intent, some of them qualitative, some of them fairly theoretical, has made remarkably little difference. Okay? It seems to be true, as I said before, that most women, at least, decide to major in physics when they're in high school, and 0.2% of high school girls think they want to be a physics major. And remember that our undergraduate curriculum is set up more to lose people than to gain people. So we're working with a small pool to begin with, and the number, 0.2%, has not changed since 1971. So I think this is fairly discouraging, and it isn't that I want to discourage you, but I think we need to think a little bit about the kinds of questions we're asking. Maybe the questions we're asking aren't exactly the right ones. Most of our research has been focused on the gender gap, as we call it. That is the idea that men do better in physics. There were more men. Why is this? What's wrong with women? What's wrong with physics? That kind of thing. Maybe instead of focusing on these kinds of things, we need to talk more to women students, and not just students who have chosen a physics major, but people who are not thinking about it, or people who have thought about it and changed their minds. Maybe we need to understand more about how physics looks to particularly young women. I think we need to focus less on college students, graduate students, and career physicists, not because I think that's unimportant, but because I think we actually know quite a bit about these populations of people. I think we need to know more about what high school and earlier girls or students think about physics. I think we need to focus on younger age groups. One of the review articles that I read contained this quote that I like a lot. Given the pervasiveness and persistence of these gender disparities, the causes are likely to be complex and multiply determined. I think this is fairly difficult for physicists, so at least it was difficult for me. When I started looking at female-friendly physics departments, here's what I thought. I thought I was going to study some female-friendly departments measured by the percentage of women graduates, so measured by a nice solid number, and compare that to typical departments that graduated the typical average. And I was going to find one or maybe two things that all the female-friendly departments did that the typical departments didn't. So my paper would say, well, here's what you do, right? You start a women in physics group, or you dedicate some of your space to a student lounge, or you have a Christmas party, I don't know, something, but one or two things. My friends who are sociologists and anthropologists and such were too polite to laugh, but they did clearly were sort of saying, well, Barbara, that's not how this works. That isn't how this works. What we're trying to do when we're trying to make physics a more inclusive community is change the culture of physics. And culture is complicated. And you need to do not just one thing or two things. You need to do lots of things, little things, that don't individually make a contribution, but added together and done consistently over the years do make a difference. So you need to try lots of things and keep trying. Okay? Don't put a lounge in, expect the number of women undergraduates to change in a year, and then say, well, that didn't work, and abandon it. Okay? You need to keep trying. Okay. I want to turn now to the second question, or well, it's really kind of the third question, and that is the what effect does the homogeneity of our community have on the science that we do? This kind of contradicts the way most people, or at least I, think about the history of physics. We have a sort of lone genius, great man approach to physics, right? We picture Isaac Newton sitting all by himself, no colleagues, no students, no background, sitting all by himself in the garden of his mother's estate, looking up at the moon and thinking, well, maybe the moon is falling just like the apple is falling, only it's too far away and it's moving too fast to hit the Earth. And physics was changed forever. Okay? Or a better example might be Albert Einstein, all by himself in the Berne patent office, wondering what the world looked like if you rode on a light wave, all by himself, no colleagues, no students, no mentors, and physics was changed forever. This is kind of the stories that we tell each other about the history of physics are like that. But physics actually, maybe it was like that then, but it certainly isn't like that now. I mean, think about the gravitational wave discovery paper that had hundreds of authors. And that discovery happened because hundreds of people worked on that project over 50 years. Physics is much more a group project than this great man, lone genius picture that we kind of have. So maybe we need to look at how groups function to solve problems, to understand a little bit better how physics evolves in time. So there is a group at Carnegie Mellon and MIT. They're mostly psychologists, although I think they're actually in the business office. And they are studying what they call the collective intelligence of groups. What they do is, let me say a little bit more about this. This is kind of analogous to Spearman's G score of general cognitive ability. in the early part of the 20th century when people were still thinking about about intelligence, were developing their ideas about intelligence. Spearman did a bunch of different experiments, and he found that if people were good at one particular kind of cognitive ability, they tended to be good at a bunch of them. So there was not one finely defined kind of intelligence for solving math problems and another one for playing word games and so on. There seemed to be a general cognitive intelligence. And he called that the G-score. Now, I realize that this is a controversial topic, and I'm not going to discuss all of the different ways that we can criticize this way of thinking about people. I just want to make the point that there seems to be some sort of general way of thinking about intelligence that involves a variety of different approaches to problem solving. What Woolley and Malone and co-workers did is look at groups, smallish groups of people, 2 to 5 people, randomly chosen, and they asked them to solve a variety of different kinds of problems. Okay. And they found the same kind of thing that Spearman had. That is, that if a group was good at solving a particular kind of problem, they were good at other kinds as well. And they called that a C-score for collective intelligence. Okay, so we're thinking about intelligence in a quite different way here, not about an individual's approach, but how a group functions. And that's even more obvious when you look at what this correlates to. I should also say that your C-score, once they had established a C-score for a particular group, they tried them out on a few other problem solving and found that they were good. So this was a good predictor of a group's ability to solve problems. And what's interesting about this study, in my opinion, is that is how these scores are correlated with the qualities of the group. It is not correlated, the collective intelligence, the C-score, is not correlated with the intelligence of the smartest person in the group. So a good problem-solving group is not one where Albert Einstein is sitting at the table and we're all listening to him. Okay? It is also not correlated with the average intelligence of the group members. So the best way to solve a problem is not to collect a bunch of PhDs from Harvard or Stanford. Okay? What it is correlated to is how the group functions, how equitably the group functions. Do they, when they're sitting around the table, does everyone take turns? Does everyone get heard? Does everyone contribute to the solution? Okay? That's how a group effectively solves problems, and that's what is connected to the C-score. Excuse me? Okay. It is also correlated, I should say, with the number of women in the group. The researchers suggested that this is because women are more socially sensitive and are more likely than men to say, you haven't had a chance to talk yet. Do you have something to say? Or why don't we let her finish? Okay. So this is one important thing. The way we solve problems in groups is by having an equitable functioning of the group. Okay? Everyone gets a chance to talk, everyone contributes. Then I have, there's a second study. This one was done by Richard Freeman and Wei Huang, who are economists at Harvard. They did a citation study of many, 2.5 million, it's hard for me to imagine this, 2.5 million papers, this is all fields. And one of their constraints is that everyone in the group had a US address. So we're not, well, I won't say that. They looked at the ethnic names of the authors, and in a separate study, they looked at the geographic distribution of the authors. Okay? They found that authors were more likely to work with someone in their ethnic group. So if you look at a group that has all Anglo names, or all Chinese names, or all Spanish names, or something like that, there were more of those than there were of groups that were more diverse in their ethnicity. But the groups that were diverse in their ethnicity had more citations. Okay? Now, we're all academics. We all know what that means. That means it's a better paper, a more original and interesting paper if it has more citations. Okay. So we can conclude from this that groups solve problems by allowing each person to speak and to be heard, and that they are more likely to do original and interesting work if they have a diverse group involved. Okay. So what does that imply for our very homogeneous community? I personally think it implies that a more diverse community would do better physics. Okay? More original, more authentic, more reliable, whatever criterion you want to use, I think that a more diverse community would do better physics. Okay? Now I'm going to do an example. This is Vera Rubin, the upper picture. The lower picture is her husband. I chose that because he just looks like such a nice man. I thought it would be nice to see. Vera Rubin was an American astronomer who died just a little bit over a year ago on Christmas of 2016. She was, in addition to all of the things I'm going to tell you, she was I think, our best shot for a third woman Nobel laureate. Every year, every fall, when they were getting ready to announce the Nobel Prizes, I would hope that this was going to be Vera's year, and it never was. And now we've lost her, and it's too late. So I've been sad about that, and I still am. She wanted to be an astronomer from the time that she was a child. She remembers lying in bed, looking out the window at the stars and watching them move. She said, I guess I was always interested in how things move. She didn't know of any astronomers, male or female, so she thought she could be an astronomer. By the time she was getting ready to go to college, she had heard of one astronomer, Maria Mitchell, who was a very famous woman astronomer at the time, and who spent much of her career at Vassar College. So she thought, well, I'll go to Vassar. She did, and majored in astronomy there. At a quite young age, she was 20, she married Bob Rubin, who was a physicist. I wrote another physicist at first, but she was an astronomer, not a physicist. So a physicist named Bob Rubin. And they would be married his entire life. He died in 2008, and they were married all of that time. They raised 4 children, all of whom turned out to have PhDs in science. Their daughter was an astronomer. As a young woman, at any rate, Vera lived a pretty typical woman's life for the 50s. When Bob started graduate school, she followed him to Cornell. She knew he was ahead of her, so she knew she wouldn't be there long enough to get a degree. So she didn't enter a degree program, but she took courses in physics from people like Philip Morrison and Hans Bethe and Richard Feynman. When Bob graduated and went to Washington to take his first job, she applied for a degree program at Georgetown, where she actually got her degree in, 1954. I thought I was going to have my computer right here so I could read all of these things. I didn't worry about this. And it's not here, it's in the back of the room, so I can only see this as well as you all can. She got her degree in 1954. Her thesis advisor was George Gamow. She spent most of her career at the Department of Terrestrial Magnetism at the Carnegie Institution, and most of her career studying the dynamics of galaxies, how galaxies move. And she worked much of that time with Kent Ford, who was an instrumentalist who designed some of the specialized spectroscopes that they used in their work. She wrote a memoir entitled Bright Galaxies, Dark Matter, which I think is just a wonderful title, and that is why I chose this picture of her photoshopped into a picture of a galaxy. I just couldn't resist. To do her most important work, she used an experimental tool and a theoretical tool that I'm going to tell you a little bit about. The experimental tool is the Doppler Shift. If you look at a rotating galaxy, so we're picturing that smeary thing at the top is a galaxy that we're looking at edge on, and it's rotating. So the stars on this side of the galaxy are moving toward you, and they're blue shifted. The stars on this side of the galaxy are moving away from you, and they're red shifted. So when you look at a line, you see the shift that's shown by the sort of blurry line at the bottom. I guess I should do this with the laser printer. This is the line I'm talking about. Okay? And by measuring the Doppler shift as a function of the distance from the center of the galaxy, you can learn how fast things the stars are moving in different parts of the galaxy. Okay. The theoretical tool is Kepler's third law. You all know about this, but I'm just going to say a couple of things. Kepler discovered empirically that if you compare the planets of the sun, you find that the distance from the sun cubed is proportional to the period squared. That is, r cubed is equal to kt squared, where k is a constant that is the same for all the planets. Okay? He discovered this empirically. Well, they weren't his measurements, but he just looked at these distances. When Newton developed classical mechanics, he derived Kepler's law by balancing the centripetal force that is required. We're assuming a circular orbit, mv squared over r, where m is the mass of the planet, little m is the mass of the planet, and setting that equal to the gravitational force, gmm over r squared, where big G is the gravitational constant and big M is the mass of the sun. You can rearrange that. You can see to see that V is equal to the square root of gm over r. G and m are constants as we move from one planet to another. So what happens is that the velocity is proportional to 1 over the square root of r. And we call this the radiation curve. This is the radiation curve of the solar system. On the y-axis, whoops, not doing it again. On the y-axis is the distance, the speed of the planet in kilometers per second. On the x-axis are the distances, the distance from the sun, okay? There's 8 data points. I didn't include Pluto. And you can see that looks like 1 over the square root of r, okay? Now, if we turn to a galaxy, what is interesting and different about a galaxy is that they are not, all the mass is not at the center. This is true of the solar system. Essentially, all the mass of the solar system is in the sun. So all we're doing as we're moving away is getting farther away. Okay. When we're looking at a galaxy where the mass is distributed, as we move farther away from the center, the amount of mass is also changing. So instead of just V is equal to gm over r, the mass is a function of distance. And if we pretend for a moment, it's not true, but let's just pretend, that the whole problem is spherically symmetric, then what we mean by m of r is the mass for which the distance is smaller than our observation point. So it's like there's a big sphere We're looking at all the mass enclosed in a sphere of radius r. And that gives us a rotation curve of the galaxy. But because of this m of r, it also tells us something about the mass distribution of the galaxy. So this is an example. The graph here is the velocity determined from the Doppler shift. The x-axis is, again, the distance to the center of the galaxy, and that's superimposed on a picture of Andromeda, which, to give you a sense of where we are in the galaxy. So if you start here from the center, you see that the velocity rises very rapidly as we're moving through the central bulge of the galaxy. Well, that makes sense, because the mass is getting larger. We're going, as we move away, we're enclosing more and more stars, more and more mass, and so we would expect the velocity to rise rapidly. Then when we get to the edge of the central bulge, the mass starts to drop off. Maybe that looks like 1 over the square root of r. I'm not really sure. Okay. But then right about here, something strange happens. The speed starts to rise again. It rises and then levels off. And now we're outside of the central bulge. In fact, when we get over here, we're outside of the galaxy as far as we know, right? Looking at the stars. So there's something going on here. There is mass here that we don't know about, that we can't tell by looking at the stars, right? When we're way out here, we would expect the curve to look pretty much like the curve for the solar system, because we would have thought we were outside of the whole galaxy, but we're not. There's way more mass out there that is non-luminous, that is dark. Okay. And this is our best evidence for the existence of dark matter. Okay. That is to say, there seems to be mass in the universe that isn't luminous. Okay. With great imagination, we call this dark matter. It's dark, it doesn't emit light, and it's matter, it has mass, so good name. It is not the only evidence. In fact, it isn't the first evidence. Zwicky in the 30s noticed, he was looking at galactic clusters, and he noticed that if you calculate the mass, again, using assuming that all the mass is in stars, if you calculate the mass of a galaxy in terms of its stars, it is not enough for the galaxy cluster to be gravitationally bound, okay, which we expect it to be. Okay. Another good piece of evidence that people use all the time now is what's called gravitational lensing. I tried to explain this, and I decided it was easier to do with pictures. So this is the idea of a gravitational lens. Here's some distant galaxy or something. Okay. There is a very massive thing right here, a black hole or a cluster of galaxies or something. And here we are at the Earth observing this. And when the light comes from the distant object, goes by the massive object, the light is curved because of general relativity. And we assume, as we always do, that the light comes straight to us. And so the position of the galaxy is significantly changed. Okay? This is a particularly, I think, striking photograph of gravitational lensing, because this circle that goes around the galaxy in the center is actually just one something, galaxy or star or something. And the light has been distorted to almost into a complete circle. The remaining piece of evidence for the existence of dark matter is we currently think that initial fluctuations in the distribution of dark matter in the universe is what began the condensation of ordinary matter into stars and galaxies. So if you look, this is from a Nature paper, this is the way we should be thinking about the universe. This stuff out here is dark matter. It's a big cloud, okay? And it's kind of, there are fluctuations. It's not the same everywhere, although as you can see, it's much bigger. The bright spots are galaxies. And you can see that it's sort of clumped up, and the galaxies are inside the clumps of dark matter. So that's the way we should be thinking about this, okay? Even though it's probably not. Right? We probably still, when you look in the sky, you see the bright things and you think, well, this is what we're talking about here. Okay. What is it, this dark matter? Well, originally, people thought it was normal matter that isn't luminous. You know, black holes, dark galaxies, neutron stars, that sort of thing. Just regular matter that for some reason isn't emitting light, so we don't have any way of seeing it. That's been looked for by other methods like gravitational lensing and not found. So it's probably not normal matter. Neutrinos were a popular candidate because when people were first starting to think about neutrinos having mass, because even though they're quite light, there are lots of them, but there seem not to be enough to comprise dark matter. So it's probably something new. Okay? It's probably not normal matter. It's not electrons and protons and neutrons. It's something else. And we have some candidates, which I'm not going to tell you. I mean, there are many candidates, and I'm not an astronomer, so I'm not going to tell you very much about them, but I'll mention them. Oh, I should have said that about our current cosmological theories say that almost 85% of the mass in the universe is dark matter. Okay? So one way of thinking about this is we didn't know what 85% of the matter in the universe, we didn't even know it was there, let alone what it is. Okay. So one candidate are called WIMPs, and I have to admit I selected this because I really do think it's a funny name. It seems to be an exotic particle. It stands for weakly interacting massive particles. They interact only through gravity and the weak force, with normal matter, that is. Maybe they have something to do with supersymmetry. So they're massive, they don't emit light, they don't interact with electromagnetism at all, and they interact very weakly with ordinary matter. This makes them hard to find. And many of the searches for dark matter, they carry them out in the same way that they carry out searches for neutrinos, right? Big, huge vats of xenon or something in the bottom of a mine, okay, so that you can screen out all the other cosmic rays and things. There are many experiments underway. Some of them they call direct detection. You're looking for the recoil of a dark matter particle interacting with normal matter in your detector, and this is hard to do. Okay. Another possibility might be to let the dark matter particles interact with each other and decay and look for the decay products. There are some experiments at colliders like the LHC to produce dark matter particles and then study the decay products. But I spent quite a bit of time reading about this, and we don't know what dark matter is. There are many experiments. Some of the best experiments have not, some of the best candidates, for the existence of dark matter have been ruled out by the experiments. Okay. So why do I think dark matter is interesting in and of itself, but why did I choose to talk about it in this talk? That is to say, why do I think this is a good example of diversity? Well, I do because the reason Vera Rubin chose to study the outer parts of galaxies was because she was a mother with small children. The hot topic of the time was the inner parts of galaxies, but she didn't want to or didn't think she could compete because of her small children. So she wanted to choose a little corner of astrophysics where she thought she could just do her work and wouldn't have to have people bothering her and trying to scoop her and so on. And as a result of this choice, she discovered something really important. Okay? We usually think of motherhood as something that interferes with our careers. And in this case, the fact that Vera was a mother created or did some of the best work she ever did. She did a lot of work, and this was not the only thing, but this is the most important thing. And when you read, why didn't Vera Rubin win the Nobel Prize, which there were many articles of last year, they always talk about dark matter. So the fact that she was different from other astrophysicists made her physics better. Okay? Made her physics unique and made everyone's physics better. Okay. So here are my conclusions. Women and members of minority groups are underrepresented in physics. I don't think there's very much disagreement with that. The numbers are pretty convincing. We don't understand the reasons for this. I wish we did, but in fact we don't. The reasons are likely to be complicated, and there are likely to be many causes and many explanations. The second thing is the homogeneity of the physics community limits the physics we can do. And that means that diversity is a valuable resource. It's a valuable resource for individuals, it's a valuable resource for our community, and it's a valuable resource for physics. I want to say one more thing, because when I was making this talk, I realized it's kind of a downer. You know, we're 40 years of research in gender gaps, and we don't know what's causing that. And 85% of the universe is missing, and we don't know where it is. This seemed like not a good place to stop. So I thought I would finish by suggesting what I think you can do. I know you're all doing these things, so I don't mean to be insulting. I hope that there will be some ideas here that you haven't tried. Okay. First thing is, learn about this stuff. These are interesting and important ideas, and some of them are quite difficult. So approach it like you approach a piece of physics. I don't think it's as hard as quantum mechanics. I don't think anything is as hard as quantum mechanics. But it is as hard as, say, electromagnetic theory. You did learn that. You could learn how to understand things like stereotype threat, microaggressions, intersectionality. Those are some of the ways that people are talking about diversity and inclusion in general these days. I mention implicit bias explicitly because I think that's a topic that physicists have a lot of trouble with. This is based on many conversations about diversity with other physicists that I've carried on over the last decade or so. I don't think physicists really believe in implicit bias. So when you talk about racism and sexism in the physics community, people tend to think that I'm accusing them of being deliberately a racist and sexist. They get mad, they get defensive, they stop listening to me. So I would urge you to try to understand what implicit bias really is. Okay? Don't get defensive. There is an implicit bias test that's online that I wrote down the website there. Try taking the test and see what it's like. Okay. In your department, try to hire diverse faculty. Role models matter to the students, and having a diverse community means you'll be doing better work. So make an effort to hire a diverse faculty. If you are hiring particularly women, having family-friendly institutional policies is a valuable thing. So try to do that. Okay? That is, push your administration, try to convince them that family-friendly policies pay off. They do. Okay. Warm up the department culture for all of your students. This is one of the things that I found when I was studying female-friendly departments. Female-friendly departments are not ones that single out women for special treatment. They are departments that have a warm, friendly, welcoming environment for all of the students. It works well for male students. It works well for women students. It works better for women students. So, and there are many ways that you can do that, right? You can start a woman in physics group. You can plan activities that will give the students an opportunity to interact with each other and with the faculty informally. Outreach activities are particularly nice because the little kids love it, and it gives the students a chance to develop a physics identity, to think of themselves as professional physicists. You can use interactive pedagogy in your classrooms. There's some data that suggests that's more attractive to women and members of minority groups. You can have a broad view of what constitutes a good physics major. Again, we tend to think of physics as something that you do well at because you're brilliant. And I don't disagree that brilliance exists, but if you can believe and emphasize to your students that hard work and persistence pay off, that they'll get better, then that will be more attractive to people who are having trouble with physics, okay? So they don't give up thinking, well, I just can't do this. If you tell them, you know, well, yeah, I got a C in quantum mechanics when I was an undergraduate, and, you know, which is in fact true. Look for, in your classes, examples of women and minority physicists. You have to kind of search because it's such a white male-dominated community that if you just randomly pull some figure from the history of physics, he will most likely be a white man. There's nothing wrong with doing that, but go out of your way to talk about Vera Rubin or I can't think of anybody else right now, but that you can find women and minority physicists if you look for them. And if you talk about them and talk about their work, that will be encouraging and provide role models to your women and minority students. Thank you all very much.
I do think we have time for maybe one question, but I know there's a session starting at 1 o'clock. If anyone has a question, please come up to the microphone.
Hi, I don't really have a question. I thought your talk was great. I just wanted to mention that the American Institute of Physics, through the Niels Bohr Library and Archives, has a whole lot of lesson plans, teaching plans on women and diverse scientists, the history of their discoveries, and they're all packaged and ready to go. So I just wanted to put in a plug for that.
Thank you. I should have mentioned that.
And congratulations.
Thank you.
I think one of the things that's most interesting about this talk, as Barbara said, it does feel a little depressing. But the hope is that we all have a part to play and we can all make it better, no matter what our specialty is, no matter what our interests are, no matter what our own background is. So that gives us hope, and that's a good thing right now. So let's thank Barbara again.
Thank you.
We'll call this session to a close. Congratulations.
Thank you.